All right, so good morning, everyone. My name is Kanah Smith. I will be completing my final year of undergrad at the University of Toronto, majoring in astronomy and astrophysics. And so this summer, I've been working with Lisa Bugnet and Arthur Lisseau at the CCA on an astroseismology project titled Unveiling Stellar Nature Through Oscillatory Pattern Recognition. All right, so we've been researching red giant stars for this project. And these are stars that have evolved off of the main sequence right here. And for reference, the sun is currently a main sequence star. So during this evolution, the star's convective envelope or outer layer begins to expand while the radiative core begins to contract as it continues on to its next evolutionary phase. And for this project, we are looking to classify 4 different types of red giant stars. Those include red giant branch stars, red clump stars, secondary red clump stars, and lastly, low amplitude or depressed stars. And so these depressed stars, of which are found mainly in the red giant branch, are stars that have developed convective cores while they were still on the main sequence. And it's hypothesized that a magnetic field is induced within these stars due to the driving of plasma in a dynamo effect. Right. And so here we are looking to classify these stars based on their oscillation patterns. But what exactly is an oscillation pattern? I just spoke about the stars having convective interiors, and this creates turbulent environments, inducing both acoustic and gravity waves in the star. Right. And so these waves are shown traveling through the star in both images. And illustrated on the left of the second plot, we have the acoustic waves traveling through the surface, near the surface of the star, which gives us more shallow characteristics, while gravity waves, illustrated on the right of the second plot, give us characteristics of the deep stellar interior. And so acoustic and gravity waves increasingly couple, known as mixed modes, during stellar evolution, and this happens inside of the cavity between the radiative envelope and the convective core. And so this is because, again, the core is contracting and the envelope is expanding. And the result is that the acoustic and gravity waves begin to couple within this region as the frequencies between the two become more similar. Back here. And so the focus of this project will revolve around the dipolar mixed oscillation mode, L equals 1, that travels directly through the stellar core and is seen on both plots here. Additionally, the parameter L simply denotes the number of surface nodes that a wave has as it travels through the star. So, like our title states, the objective of this project is to classify red giant stars based on their oscillation modes. So stars will present different degrees of coupling in that L equals 1 oscillation mode based on their evolution, which is why L equals 1 has our focus. On this figure here, we can also see that region between the core and the envelope where the coupling between the acoustic and the gravity modes occur. So to get started on our work, we obtain our data from the Kepler Space Telescope, which hunted for exoplanets using the transit method, which can be seen on this plot right here. So by monitoring stellar light curves, we wait for a planet to pass in front of the star and decrease the light, and then we know that it's a planet, and so they search for planetary systems using this method. And so because of this, we now have light curve data for our red giant stars. Okay. And so to get started on our work, and now you may be wondering how these light curves fit into the context of our project. And so the oscillation modes I mentioned earlier cause the amount of light emitted by the star to flicker in time, but within specific frequency ranges. So when we take those light curves and translate them into the frequency domain using a Fourier-like transformation, we get what is known as the power spectrum density diagram, which is just up here at the top. And so highlighted here, we have the region where the star is oscillating, although it's not clear on this diagram exactly which region in which the star is oscillating. And so the next thing that we do is we put this same power spectrum density diagram into a logarithmic space. And when we do that, we're more clearly able to see the active region where the star is oscillating by the bump that is highlighted there. And so highlighted here, we have the region where the star is oscillating. And so now we can see a more well-defined active region. And so when we magnify this region, we see the oscillation modes L equals 1, L equals 0, and L equals 2. And again, these numbers just denote the amount of surface nodes that the wave has as it propagates throughout the star. And this visual right here is just an illustration of how those modes manifest on the surface of the star. Right, and so now with this magnified power spectrum density, we create what is known as an Echelle diagram. And we do so by vertically slicing our diagram by a parameter delta nu, which simply denotes the distance between consecutive L equals 0 oscillation modes. And then we take these slices and we stack one on top of another like a ladder, hence the name Echelle, which is ladder in French. And so the bright spots here represent the high points of amplitude from the power spectrum density diagram that we have there. And we can tell by looking at the L equals 1 oscillation mode that this example here we have is a red clump star, because our L equals 1 oscillation mode is showing light scattering. And so here we also have the Echelle diagrams for all of the stars that we are trying to classify. And so in contrast, we have all of them. And so from left to right, we have the red giant branch stars, which shows slight scattering, but is mostly linear in that region. Again, we have the red clump star. Next, we have our secondary red clump star with more prominent scattering. And lastly, at the end there, we have what is known as our low amplitude or depressed oscillation mode stars with no visible L equals 1 oscillation mode. And so again, it's hypothesized that an interior magnetic field is trapping the L equals 1 oscillation mode inside of the star and not allowing for it to be expressed on either the light curve, the power spectrum density diagram, and then consequently our Echelle diagrams. And so now that we have our Echelle diagrams generated for each of the stars, we can begin our classifications. So first we feed our Echelle diagrams to a convolutional neural network deep learning algorithm developed by Google, and it is called Inception, and its purpose is for image and object identification. And the typical output of this algorithm is a classification based on the algorithm's image library, but since it's unfamiliar with our Echelle diagrams, we instead take the penultimate layer from the neural network, and this gives us a long 1D vector that is weighing the image characteristics. All right, and then we take this long 1D vector and we reduce it using TSNE, which is an algorithm for multidimensional data analysis. And then the output of this algorithm is a 3-component vector, which we finally feed into a spectral clustering algorithm called nearest neighbors. And this essentially groups our 3-component vectors for each Echelle diagram based on their proximity to one another. Okay, and so with the classifications complete, we now have our results. And so the image here is a 2D projection of the 3D map that was created using those 3-component vectors. And each color here represents a group of red giant stars that have unique oscillation patterns. And so when we initially receive the data, the clusters are undefined, but the plots that we have, just like on our computer, are interactive. And so when we hover over each of the clusters, we're able to, it shows us exactly which the different types of Echelle diagrams have been classified into each region. And so with that tool, we're able to label each of the clusters for their evolutionary stages. Right, and so here we have our main classification for the project, where we can see clusters for the red giant branch, the red clump, our secondary red clump, the depressed stars, as well as a few unclassified regions, which are the black, the red, and the yellow. Right, and so similar classifications to ours have been done previously with Han, Stello, and Yu from 2017. They had used magnified power spectrum density diagrams seen here and fed them into their neural networks. And so their network was trained specifically to classify stars as either being red giant branch or red clump stars. And our classification differed from theirs because instead of feeding our neural network with the power spectrum density diagrams, we instead fed them with our Eshel diagrams, which present better oscillatory characteristics so that the neural network is better able to classify diagrams. And so here we can see a comparison between their previous classification and ours. All right, and I think I went too far. Yeah, all right, so this is just the final conclusion slide where we have a direct comparison, and we can see that we were better able to classify the data set that we have. And additionally, we did have more data than they did. All of their gray points on their plot are indicative of the data of the stars that they had that didn't have the proper astroseismic parameters to be able to do the classifications, as this came out in 2017, I believe. But to date, we have those parameters, which is why we were able to classify more. And so they classified about 14,000 Kepler red giant stars, and we were able to automatically classify around 18,000 of them instead. All right, and so I'll leave you with this slide, and thank you for all of your attention. I'll take any questions if you have them.
All right, any questions in the room for Kanah? Yeah, Zach?
Hi, thanks so much for your talk. This is really cool. So for the shell diagrams, how did you know in the PSDs which ones were L equals 0 and which ones were L equals 1 and which ones were L equals 2?
Thank you for your question. I think that's a great question because it kind of makes you not want to do their approach because you kind of wonder how is the machine, because I guess like you can say the machine sort of works the way that we work in terms of image classification. If we can't easily identify how what those oscillation modes look like in this diagram, all the way back here. If we're not able to easily identify the oscillation modes in this diagram here, how is the machine able to do it? So that's why we instead did the shell diagrams. But when we look at the power spectrum density, Lisa mainly helped me to assess which ones, but there is a doublet sort of system. So we can see on the shell diagrams that the L equals 2 and the L equals 0 oscillation modes are very close together. And when we also look at the power spectrum density, there's like a pointer thing up here, right? Yeah. If you look very, very closely, there's like a doublet system where you can find these oscillation patterns. And then once you find, so L equals 2 is here, L equals 0 is here, and then L equals 1 is just over here. And once you find that pattern, once you find a singular pattern, it'll repeat in equal increments, which is why we're able to slice them by that parameter delta nu. So like all of the L equals 2 are equal distance from one another, and that's the same with all of the oscillation modes.
Okay. Other questions? All right. Yeah, Professor Gates?
Well, again, thank you for the presentation. I was wondering about those waves that were sort of in the upper atmosphere of the stars. Mm-hmm. What determines if there's a comparable depth to which those go? What do you know? What determines that behavior?
In terms of the depth of the waves that are propagating throughout the star. Yes, so some of it is determined by the evolutionary stage of the star, which is why we wanted to assess those waves, because as the star gets older, the core will contract, the envelope will expand, and when the envelope expands, those waves that are typically more shallow will increase in frequency because it's getting bigger, and then those waves that are propagating through the core are going to get higher in frequency because that region is getting smaller, and so that can change things as well as just the interstellar material that's inside of the star will also determine how deep those waves are able to propagate.
Thank you.
Okay. I think we should move on to the next speaker. So let's thank Kanah one more time.